Hello, welcome to everyone. Welcome back to my YouTube channel. So, in this lecture, I will teach about the chemical shift value of these organic compounds. So, only a single atom proton peak should be expected from the interaction of the radio frequency energy and strong magnetic field on an associated isolated proton. But the organic molecule have different kind of protons having different electronic environment in the molecule. So obviously, then it is the electronic environment that determines where the proton should absorb in the spectra. So the position of the signal indicate the electronic environment of the different kind of proton present in the molecule. So that means in a in a organic molecule, the proton and different proton have different chemical environment. So the chemical shift of this proton will be affected to the chemical environment of this proton. So that will get in the NMR from this chemical shift value we can assume or we can identify the chemical environment of this proton from this NMR spectroscopy. So we have already pointed out that when the magnetic field is applied to the electrons around the protons are induced to the circulate and is going to generate a small secondary induced magnetic field. So it acts as a opposition to the applied magnetic field. So we have the following situation. So that means when we applied a magnetic field in around around the around the proton there is an electron. So electron will circulate generate a secondary magnetic field. So that will opposition to the applied magnetic field. So eventually when then a proton experience the magnetic field of strength less than V0, thus the absorbed radio frequency at which the instrument operate, we have to increase the strength of the applied magnetic field in such a limit that ultimately the proton should experience the magnetic field of strength V0. Such proton is shielded by the circulating electrons, and eventually such proton will be give a signal at higher magnetic field called the upfield. Eventually with a decrease in the electron density around the proton, that will deshielding effect, the proton will appear at the downfield with respect to the former. So that means a proton is maybe deshielded or shielded. So when there is a more electron density, when is more electron density, so that means the proton is shielded by the electron. So that case the proton is called the in the upfield shift. And when there is a less electron density, the proton is deshielded, so that proton will be appear at the deshielded more negative downfield NMR chemical shift. So as a result, we have been point out the convenience that we are need of the reference point or better reference compound as a standard from which amount of the upfield shift or the downfield shift of our proton in the under study can be measured. Such reference compound is a tetramethylsilane. So here in the NMR tetramethylsilane, we choose tetramethylsilane as a reference point. So according to this reference chemical shift value of the tetramethylsilane, we can consider the upfield and downfield shift of a given molecule. So now, because of the low electronegativity of silicon, the shielding of the proton of the tetramethylsilane is greater than the most of the organic molecule. So as a result, NMR signal of particular proton appear at different field strength and usually lower than the TMS. So this called the chemical shift is measured not in the units of field strength, is might to expected in the equivalent frequency. So that means the phenylsilane, the proton of the phenylsilane is more shielded. So all the organic molecule mainly comes at the downfield to the corresponding to the proton shift of the phenylsilane. So here the chemical chemical shift value is dependent upon the difference in the calculated frequency divided by radio frequency at which the instrument operates. So eventually the delta mu is the difference is the calculated frequency of hertz of the sample and the reference of the current percent applied magnetic field strength. And eventually by the dividing the mu delta mu with the radio frequency with the megahertz at which the instrument operates, same chemical shift value is obtained for applied. So 30 megahertz, 300 megahertz, 600, so peak will appear at the same position of the spectra for any instrument, and for which it is called the universal. So common chemical shift value delta values which are always written from the left to right, and TMS signal would be the extreme right on 0 by the deviation. So here the phenylsilane TMS value is marked as a reference point with the 0. So in this case it is a Dowell field with the increase of the delta value, which is in ppm. So point noted that numerator is expressed in hertz and denominator is megahertz. So delta is thus expressed in ppm. The following table show roughly the characteristic photon chemical shift. So cyclopropane has the chemical shift value is 0.2, and the primary, secondary, and tertiary CH proton have the chemical shift value 0.9 to 0.15. So tertiary have the more chemical shift value compared to the primary, and this is the phenylic proton comes as a 4.6, or so this is the table for the proton shift value of the corresponding proton. So like that, the aldehyde CH proton is chemical shift is 9 to 10 region, or the carbon acid COH proton comes as a 10 to 12 region, or the aromatic CH comes at a 6 to 8 region. So now we will discuss the factor that influencing the chemical shift values. So we have already pointed out that the chemical shift for a proton is determine the electronic environment of this proton. So these depend on the following factors. One is the inductive effect of the electronegative elements, the diamagnetic anisotropic effect of the chemical bond, and the hydrogen bonding. So mainly these three factors determine the chemical environment of a given proton. One is the inductive effect of the electromagnetic element, on the diamagnetic anisotropic effect of the chemical bond, hydrogen bonding. So now I will discuss about the inductive effect, how the inductive effect will affect the chemical shift value. In an organic compound, proton is covalently bonded to the carbon, so nitrogen, oxygen, or other atom by a sigma bond. When placed a strong magnetic field, the electrons of the sigma bond circulate to generate a small magnetic field, which opposes the applied field. A nearby electromagnetic atom withdraws the electron density from the neighborhood of the proton, so that a small applied field is needed to cause the spin state of the proton to fill. The signal is for a deshielded proton is observed downfielded, then the signal of the proton that are deshielded by the electronegative atom. So that means when there is a more electronegative atom present in the molecule, so that will withdraw the electron density, so that proton is a more deshielded, so that will be more negative value compared to the other. So let us consider the following example, where the CH3F, CH3Cl, CH3Br, so CH3 so here CH3F has a more downfield shift 4.26 compared to the chlorobromoiodine. So here the reason is this: among this fluorine, chlorine, bromine, and iodine, the fluorine has more electronegativity compared to the chlorine, compared to the bromine, or compared to the iodine. So here for the chemical shift of the protons of halomethane is directly related to the electronegativity of the halogen atom. So here the electronegativity increase from the iodine to fluorine. Here in this way, so here the fluorine has more minus I effect. So that means the fluorine is most effective at the withdrawing electron density from the methyl group. So therefore, the proton in the fluoromethane are the most distilled than any of the proton in the series, and thus the signal is found to fastest further downfield at 4.26. As iodine is the least electronegativity halogen, so the signal in the iodomethane protons and found to furthest upfield is 2.16. The signal of the proton of the chloromethane and bromomethane are intermediate. So that means with the more electronegative fluorine, the more the withdrawing of the more electron density, so that will more downfield. And so here the chemical state value delta is more for the fluoromethane. So next, a similar situation prevails the methyl proton attached to the carbon, nitrogen, or oxygen or other electronegativity element of the periodic table. Since the order of the electronegativity of the carbon, nitrogen is the carbon is the least electronegativity compared to the nitrogen compared to the oxygen. So oxygen is a more electronegative. So the methyl proton attached to them move to downfield due to the increased descending effect of the electronegativity atom. So here, when methyl group is attached to the oxygen, it will be more downfielded, so it has more downfield shift value 3.3, and compared to the nitrogen which is 2.2, and compared to the carbon which is 0.9. So that means oxygen has more electronegativity, so it will withdraw more electron from the methyl group, so it will be more downfield. Furthermore, in otherwise equivalent environment, the more number of the hydrogen atoms to one carbon, more the magnetic shielding. Hydrogen is the greater electropositive than the carbon, so that will result that every replacement of the hydrogen by an alkyl group causes a downfield shift in the resonance of the proton. Thus, the proton containing the methyl, methylene, or methane carbon comes successfully at the downfield region of the NMR spectra. So that means when they compared to the methane, when the hydrogen atom is successively substituted with the methyl group, so that will the more downfield shielded, so that they will give more downfielded value of the chemical shield value compared to the methane. So that now, as we know, the inductive effect decreases with the increase the distance of the electronegativity element from the carbon center. So the magnitude of the downfield shift of the protons become lower comparatively along on the carbon chain. Thus, the N-propyl chloride has the three set of non-equivalent protons, and we have the following delta values. So that means inductive effect also depend on the distance of the negative element to the carbon center. So that means when the electronegativity atom attached to any carbon center, the distance will when the distance will increase, the inductive effect also decrease. So that means that proton will be more upfield. So here for the 1,4-propane, so this hydrogen is directly attached to the chlorine, so it has more delta value, says 3.3, and for this case it is a chlorine is far away from this proton, so that will more upfield, so that has more upfield delta values is 0.9. So now the propane contain two sets of non-equivalent protons. A signal is obtained for the two terminal CH3 protons at the normal region 0.90, and another signal appear at an intermediate methylene group delta is equal to 1.33. But however, in case of the next example is 1,3-dichloropropane. So in the case of 1,3-dichloropropane, it has two sets of non-equivalent protons due to the presence of electronegative chloride at the terminal carbon. The electron withdrawing effect of the chlorine lower the electron density in the vicinity of the terminal methylene proton. So the downfield shift is caused by the minus I effect of the chlorine atom and the terminal methylene proton being deshielded and resonance at 3.58. Another signal is obtained in intermediate methylene, which is slightly downfield at 1.85 in the normal region as the inductive effect decrease along the CC bond distance, which lowers the deshielding effect over the protons. So we have the following observation. So here 1,3-dichloropropane, these two hydrogen is equivalent. So these three hydrogen is directly connected to the chlorine atom. So these two hydrogen is more downfield compared to the this hydrogen. So here these two hydrogen has a more downfield shift, value is 3.58, and here the inductive effect is decreased due to the bond distance. So here it has more less downfield compared to the this, so it has value as 1.85. so now also the again with the increase of the number of the electronegativity atoms, electron withdrawing effect is highly increased, the proton are expected to move to the maximum downfield region. So in this example, that means in this example in this region, the number of electronegative bromine atom will increase. So in this case, there is total 3 bromine atom. In this case, there are 2 bromine atom. This is case only on bromine atom. So when the number of the electronegativity atom it will increase, so that it has more minus I effect on this carbon. So that photon will be more decelerate compared to the other. So here when the 3 bromine atom is substituted of the methyl group, so here this proton is a more decelerate, is it have delta value at 7.04. when and when this is 2, it is least it is less compared downfield compared to this, so it has value at 5.0. and when this is 1 bromine atom, it has 2.82, and here no bromine atom, so it has least downfield, it is compatible upfield, so it is a 0.23. Similarly, in the situation for the phenyl system, phenyl nucleus has minus I effect, which cause the high descending of the benzyl benzylic proton. In the case of the toluene, methyl proton of the benzylic position absorbed at high downfield shift at 2.34 than the normal region. Again, the increase the number of pH increase in nucleus, descending parameter increases to get such downfield shift of the corresponding benzylic proton in the following system. So in this example, phenyl group has the minus I effect. So normally the benzylic position CH3 is comes as a more downfield compared to the normal sp3 CH. So here due to this is because due to the minus I effect of the phenyl group, so it is more downfield compared to the this CH4. When the number of phenyl group is increased, the in the downfield shifting is the increase. So here when the 3 phenyl group is present, it is more downfield, which has value as 5.63, and when 2 there is 3.92. So in this connection, it is worth mentioning that the TMS silicon is a rather electropositive with respect to carbon. So as a result, all equivalent methyl protons of the TMS will be shielded highly and therefore resonate at comparatively higher applied magnetic field strength with respect to common photons of the organic molecule. So set up the NMR scale, TMS peak 0 as charge is set to the right-handed edge. Now we could make a good number of estimate as a chemical shift using the concept of electronegativity. So if the inductive effect is the only deshielding or shielding mechanism operating, then we expect that delta value of the ethane, ethylene, and acetylene will increase as a regular way as the change in the hybridization of the electronegativity increase. As a result, the proton are expected to deshielded according to the giving downfield shift. But the reality, the compound absorbed, the ethane has the delta value is 0.9, and the ethylene has 5.84, and acetylene has 2.88. So here from this 3 example, we can tell that only the inductive effect is not the factor for deshielding or shielding of a proton. So from this evaluation, it is clear that shielding experience by the acetylene in comparison to ethane is not only the effect of the electronegativity. This anomaly can be explained on the basis of other factor known as the diamagnetic anisotropic effect. So next we discuss about the diamagnetic anisotropic effect. A magnetic field is induced by the action of a magnetic field is induced by the action of applied magnetic field B0 on pi electron. This magnetic field is induced by the pi electron in the direction in nature. So this known as the diamagnetic anisotropy, which means the shielding and deshielding depend on the orientation of the molecule with respect to the applied magnetic field. So these effects are the contrast to the inductive effect, which is symmetrical around the photon. In addition, the anisotropic is also applicable to the sigma framework. So in case of ethylene, the external magnetic field causes a diamagnetic circulation of the pi electrons. So this produce as shown below in the induced in magnetic field in the between the double bond of the atom that oppose the applied magnetic field, and the same time that induced magnetic field in the region of the olefinic photon reinforces the applied magnetic field. So here the a pi electron from this pi electron from this the circulating magnetic field. So here the induced magnetic field oriented in the same direction as the B0 around the vinylic proton. So it is a this region is called the shielding region, and this called the resultant paramagnetic field. It is called the deshielded region. So thus any group attached to the olefinic bond is deshielded because the diamagnetic anisotropic effect in the plane of the carbon-carbon double bond. So that means the deshielded region, this is the deshielded region is placed in the plane of the carbon-carbon double bond. So and the shielded region is pointed out to the double bond. So the large difference in the absorption position of the alkene and alkene photon in the combined effect of the increase the electronegativity and as well as the diamagnetic anisotropic effect. So as a result, ethylene photon absorbed at the high downfield region at delta is equal to 5.84, whereas the photon of the ethane absorbed 0.90. So this is the 1 NMR of the ethane. So here the 0.90 peak present. This is a highly upfield shift, and for the ethylene we got the 5.84. So this is the downfield shift due to the deshielded region. So but in the case of acetylene, the photon, the situation is slightly different. The molecule is the linear and the triple bond is symmetrical about the axis. So this axis is aligned with the applied magnetic field, and the pi electrons of the bond can circulate the right angles to the applied magnetic field. So thus the induced magnetic field is diamagnetic in nature and oppose the applied magnetic field along the C alpha axis. Since the photon lying in the along the magnetic axis, it is shielded by the induced magnetic field and the circulating pi electrons. Thus, the higher applied field is required for bringing back the alkyne proton to resonance. Though the electronegativity of acetylene increased, but due to the pronounced diamagnetic anisotropic effect, the acetylene proton are shielded and absorb upfield shift delta at 2.88 with respect to the vinylic proton. So that means here the shielding region is around the CC triple bond axis, and and so here the proton is lie in this shielding region, so it is more upfield compared to the vinylic proton. So this is the NMR spectra of this ethyne molecule. So ethyne molecule has a delta value as the 2.88, which is comparatively upfield compared to the ethylene. So now the absorption position for the methyl group of the pinene and alpha pinene and the beta pinene are given follows. So pinene has the delta value is 1.01 and alpha pinene has the delta value is 0.85 and beta pinene has the delta value at the 0.72, and this hydrogen has the 4.65. So in case of pinene, we get the normal chemical sheet value for this methyl proton but in the case of methylphenane, this CH3 group is in the this CH3 group, the methyl group attached to the double bond. A double bond is that this CH3 is the attached to the double bond is in desilted region, so it has more downfield shift compared to the normal penane. But for the methyl proton of alpha penane absorbed at the downfield shell. This effect the result decrease the diamagnetic shield of methyl group attached to the more electronegativity double bond and also diamagnetic anisotropic effect. But this CH3 group is in the shielded region of this CC double bond, so it is more shielded. So there, that's why the delta value is 0.85 for this case compared to this. But for the beta penane, this CH2 is a more downfield shift region, so it is has more delta values at 4.65, and this is normal come as 0.72. So 1 ME absorbed in such upfield at 0.85 compared to the corresponding ME penane because of the rigid structure of the molecule force the lies close above the pi electron of the double bond. So methyl beta of the alpha penane is the shielding zone of CC double bond and resonance at higher field due to the diamagnetic anisotropic shielding effect of CC double bond, where the methyl C of the alpha penane appears as a normal region being far away from the shielding region of the CC double bond. Similarly, in the spectrum of the beta penane shows an abnormal shielding effect. One of the methyl group, the BZ isopropyl group of beta penane absorbed at 0.72, which is at higher field than the corresponding methyl of alpha penane. The methyl B of the beta penane also falls in the diamagnetic shielding zone of CC double bond. So examination of the molecular models reveals that this the beta B methyl group is closer to the summary symmetry axis of the pi electron clouds of the double bond in case of beta penane than in case of the alpha penane. Thus, the shielding would be exposed to be greater as beta penane is further away from CC double bond. Its resonance is normal region at delta equal to 1.23. So eventually, these two isomers of penane can be distinguished mainly from the difference in the chemical shift of the methyl group of the two isomers. So let us consider the in case of aldehyde. So a proton of the aldehyde groups absorbs at much lower field, which is 9.97, than would be the predicted on the grounds of the electronegativity. So there are some other factors that are the electronegativity concept is to be considered. Thus, this expected deshielding position of the aldehyde proton can be rationalized considering by the diamagnetic anisotropic shielding effect. So here so induced magnetic, so here the induced magnetic field in the line along with this applied magnetic field. So induced magnetic field oriented in the same direction of the around phenylic proton. So here this hydrogen is in the deshielding region, and where this deshielding region, so here the carbonyl C group is oriented such a plane that the trigonal carbon atom perpendicular to the applied magnetic field circulate of the pi electron. The group produce an anisotropic effect at the proton that result in the deshielding. The exceptional downfields of the aldehydic proton is combined the effect of the high electronegativity of the spt carbon of CO2 and minus IF of the carbonyl group and the diamagnetic anisotropic effect. So that means the more downfield shift of the carbonyl hydrogen is due to the total three effects. One is the more electronegativity of this O bond, CO bond, and the anisotropic effect, and the sp2 carbon. Let us discuss the NMR spectra of the acryldehyde and alpha beta unsaturated carbonyl compound. At first glance, the olefinic protons of the alpha beta unsaturated carbonyl compound are expected to be in the diamagnetic deshielding zone, but two beta hydrogen of the alpha beta anisotropy couple is expected to resonate a different field due to the diametric anisotropy of the carbonyl group. Let's close a loop of the following figure. So here total in the case of acryldehyde, the proton which is the beta sees to the carbonyl group falls in the desilting zone. So this C double bond O also resonates downfield compared to the normal proton which is beta and turns to the carbonyl group B, which is away from the desilting zone. So it appears a normal region. So that means, so here this HA, this beta hydrogen is come closer to the desilting zone of the C double bond O. So this is more downfield, and this HB is far away from the desilting zone. So it is more upfield and comes as a normal zone. So this is the NMR of this acryldehyde. So here this due to the more desilted, this hydrogen comes as 6.27 and this hydrogen is 6.0. So similarly, considering the case of 3,3 dimethyl acryldehyde, the protons of the methyl group, which is beta and cis to the carbonyl group, resonate at lower field than those corresponding to the proton of the methyl group, and the beta turns to the carbonyl group. This is fact that in the case of methyl proton fall more close to the desilting region of the C double bond group than the methyl protons of the other groups, which are far away from the desilting zone of the C double bond group. So that means this CH3, the hydrogen and proton, the proton is come closer to the desilting zone of this CC double bond, CO double bond. So this is more desilted, and this CH3 group is far away from the desilting zone of the C double bond. So this is the down in the shielded zone. So that means, so that's why it has the value 1.94 and it has value 2.16. So this is a desilted zone of the CO double bond, and this is the far away from the desilted zone of the C double bond. So this is the more upfield shift. So now we will discuss the NMR of the paraxylene. So paraxylene has total two sets of proton. One is the methyl and another is the hydrogen. So point to note that the paraxylene have the only two NMR signal. So this is simply due to the fact that there are 22 types of proton, namely 6 equivalent methyl protons and 4 equivalent aromatic protons. Here the height of the peaks is the ratio is 6:4, indicating that the number of two types of proton. However, it is worthwhile to note that the aromatic proton, which is a major downfield with the delta halus, the gamma 7.1, those are the highly desilted. Thus, the question arises why this is so. So we are now ready to answer the question. Aromatic system have so in this paraxylene there are two types. One is say methyl and one is aromatic proton. So aromatic proton has the value as 7.11. So it is more desilted. So why this aromatic proton is more desilted compared to the vinylic or acetylene group? So aromatic system benzene contain large number of pi electrons. So as a result, strong diamagnetic currents are induced by the applied magnetic fields. So here the desilted region is far away. The desilted region is away from the plane of the benzene ring. So constantly, it is important. An isotropic effect is provided by the pi system of the aromatic ring. The circulating electrons have above and below of the plane of the aromatic ring are known as the ring current. So ring current creates a magnetic field opposed to the applied field beta 0 at the center of the ring. So reniforming is the applied field outside the ring. So it called the ring current effect. So here the ring current, due to the ring current effect, the desilted region is created. So is observed as the ring current oppose the applied magnetic field at the center of the ring. So above and below of the ring we get the shielding region, and any group which is strictly held above below of the plane of the aromatic nucleus will obviously the abnormally shielded because of the ring current effect, whereas the aromatic protons or any group oriented such the content plane of the benzene ring in the deshielded zone. So that means any in the benzene ring, any substituted in the benzene ring that will in the plane of the benzene ring that will be the in the shielded zone, and any group which is the above or below of the benzene ring, so that will just more shielded zone, and that will give the field shift value. So again, the methyl protons attached to the benzene ring lie in the deshielded zone of the nucleus due to the ring current effect, and therefore is expected to resonate at downfield compared to the normal methyl proton. So actually the case as the result, the benzylic proton absorbs at the region of 2 to 3 ppm according to the. So here this benzylic proton it is in the plane of the benzene ring, so that's why it is more downfield compared to the normal CH3 group, so that is more downfield, so that is give the more downfield shift value 2.35. So that's why the methyl protons of the xylene come as the 2.34 due to the ring current effect. And the compound, so this compound has a chain of 10 methylene groups linked to the para carbon of the benzene ring. Such between are called the paracyclophenes. So structural content constant, the bridging current requires the middle of the two methyl group lie over the face of the benzene ring, which is the shielding region of the nucleus. So expect the resonance high upfield. So 4 benzylic hydrogen are also deshielding region, and thus expect to resonate 2 to 3 ppm. At the same time, 4 aromatic protons are expected to happy downfield. So it is the value is the 7 to 8 ppm. So the structural features. So this is the chemical shift value. So here these all hydrogen are in the above of the benzene ring, so that means it is in the deshielded region. So these two hydrogen is more on this deshielded region, so that has more upfield shift 0.30, and in this region when this hydrogen has gradually far away from the deshielded region, so that then the chemical shift value is a more downfield, and this benzylic is in the plane of the benzene, so that is more downfield, as the chemical value shift value is a 2.55. So thank you.